So our next unit is going to be short, so you probably should look to have your next unit test by the end of next week. Probably for sure by then, maybe a little sooner. And we're back to triangles again for this unit, and actually for the next two we'll be doing triangles. And then we get to circles, which actually have a lot of triangles in them. It's kind of funny, but triangles makes up a big part of our work. So let me put the slide up here just real quick. This topic is in the book. It's Unit 7, and it's called similarity. So kind of a broad word there. But in math, we have a specific definition of what similar means, and it actually, the impact of that allows us to do some kind of interesting solving. So it's good stuff. One word that I want you to lock in right now is proportional, because in math, those two are basically the same thing. So this unit is really a unit all about proportionality and using that to either prove or solve in triangle kind of relationships. This will be the last unit that we do proofs in, so I know you're sad about that. These proofs are super easy.
Are we going to do proofs in all the units for algebra 2?
We will do no proofs in algebra 2.
Oh, we're like done now.
Yeah, this will be potentially your last proof ever. This unit.
You can study how the Earth is round.
Yeah.
Are you sure it's round?
It's not round.
Aren't the enlightened people currently thinking it's flat?
Until it just slowly
Actually, it's an
goes.
interesting feeling falling off the face of the earth.
Yeah.
Well, like,
No, it's
if,
always not.
with the
I mean, you
gravitational
die.
pull, if you fall, you would just go like this, you know?
Yes.
Travel to the other side.
Like a magnet.
No crap.
It just makes it look like you jump too high.
Just like
Your
jump
ball
and
back
then
down.
If you're watching the video, go back and do this warm up. Sorry, I forgot to record it. So solve for the zeros. Then we talked about
At the equator.
standard vertex and intercept form for a quadratic, just as a side note. And now we're
Well,
getting
by
into the
then,
content. So.
the center mass will have caused a black hole.
All right, proportion or proportional. Like I said, this whole unit is basically a unit about proportionality. So, quick reminder that proportional means an equivalent value, and specifically, we're usually thinking about equivalent value of two ratios or fractions. So, like if we said what's equivalent to 1/2, of course 2/4 is, they're both equal or equivalent at a value of 0.5. You guys remember that? The middle school curriculum is pretty heavy on proportional reasoning. Does it ring a bell at all?
Yeah.
I don't
Some?
remember middle school. It was
Okay.
so long ago.
Yeah. So we'll get back into it. You'll pick it up. These kind of are easy, right? This is like a recipe calls for 1/2 cup of something, but what if I'm doubling the recipe? Now I need more, right? So that's proportional reasoning. That's kind of the kind that you would maybe use in everyday life. But this is actually proportional reasoning. I mean, it's something that you do use throughout your life, even if you're not calling it that. It does come up. Like maybe if I could drive 200 miles on 1/2 a tank, how far can I drive on the rest of the tank? Probably, right?
I was counting my pulse.
Okay. Yeah. Well, I think I know.
Because like it did 30 seconds.
Yes, and double it. So she's talking. You probably didn't hear, but she's talking about pulse. When you check your pulse, you rarely check it for a full minute. You usually, like when I was a nurse, we usually did it like 15 seconds and just times it by 4. Right? That's proportional reasoning. I mean, obviously it could change in the rest of the 45 seconds to the minute, but you're assuming that it's an equivalent value if you just scale it up. Okay? So we're going to use the word scale factor, scale meaning that we're changing the size of something a lot in this unit. These get a little bit more complicated. We'll see this in a minute if we have something that you can't just do in your head. So, I don't know, just making this up, like 4x plus 5 over 10. Okay? Or, so there's an example of probably can't just do it in your head. Or if this was flipped over, you definitely couldn't. Okay? Because we have no idea now what the scaling factor, like here it was times 2, so we knew the numerator had to follow. Down here, who knows, right? But we still solve it, all of these we can solve the same way. Some just require a little bit more work. So why don't you grab your note packet so we can start getting some stuff put in here. And for us, let's see, I can't even remember. This is
Units.
Last
1,
one was
2,
like 4.
4, 6, 12. So this is unit 5.
Oh, I totally got it.
You did, yeah. Okay, so similarity is fairly specific to figures, like shapes and figures. And I don't want you to narrow that concept down to like triangles, parallelograms, and simple things. But like this room could be similar to Mr. Golden's room next door, even though it's kind of a weird shape, right? And actually, this concept gets used a lot in construction.
They're like, it's similar enough.
Yeah. But the whole idea behind similarity is proportional reasoning. Proportion. I feel like I'm spelling that wrong. Yep. Let's just call it proportion for now. And I guess in parentheses you could say proportional. Have you used this word outside of the math classroom at all?
Yeah.
Do you know an example of when? Cooking. How about you?
When it comes to like our family getting like a bunch of food, I say that I should get the most because it's proportional.
Okay. I see.
Yeah, bro. I need food. With half my size, she's like half my size, half my age. It's just proportional.
So this unit is based on proportional relationships. A proportion is equivalent value ratios.
Wait, have you graded my test yet?
I don't think so.
I would have taken you real.
You're unimportant.
I know that.
Okay. To make the ratios equal value, we already saw this, but let's put it in here. The question mark has to equal 2, so that both have a value of 0.5. Okay, and I want you to start thinking about decimals are helpful in this one. In this unit, I mean. Because sometimes it's kind of hard to tell if a fraction is equivalent. And we can just divide, turn it into a decimal, and then we know for sure. Let me raise this up for you. Okay, so a couple of big ideas already. So proportional is equivalent value. Typically we see that in the form of two ratios. And to check equivalence, just divide to make them both a decimal and then compare those decimal values. Any questions on those?
Can you scroll up? Just a little bit?
Like there?
Oh.
So you might grab your calculator for this, write whether each pair of ratios forms a proportion, and what is a proportion? What is a proportion?
Proportion is the unit is based on proportional relationships. That's funny. They're almost similar.
Wow, we didn't write any of that. What is a proportion? A proportion is equivalent value ratios. Maybe you should add that, Jazzy.
It's there now.
Look here. Okay, do these have the same value?
Yes.
Okay. What is the decimal?
Yep. And no, not 3.
It's 1.7.
Oh.
What's this one?
Or 1.7.
1.7.
Okay. Just real quick.
No.
I don't want you to get locked into your calculator. Just know that it's a tool. Can these be a proportion? No, because this is less than 1, or excuse me, bigger than 1, and this is way less than 1, right? So this is roughly 0.17,
No.
and this is like 1 point something, 1.1. Huh? Did you divide it?
No, I was doing that.
Okay. How about these two?
No.
No way.
Yes.
Yes.
Okay. That one's just
Divide
easy
by
to
2.
see by just using what that 2 is called the scale factor. If we did decimals, both of these are 0.4. How about these two?
No.
They look like 4.
This is times 8
Hooray, I got that.
times not 8, right?
Right.
So these are not. How about these?
Yes.
This is 1/3. That is
1/3.
1/3.
Yeah. 17 over 8.
And just
Okay.
Nope. Not by a long shot.
Definitely no.
That's like 2 point.
And how about here? That one's a little harder to just look at, right? Now you could reduce your fraction, but I feel like if you're going to reduce your fraction, why don't you just punch it in and use the decimal? Unless you don't have a calculator. What's 10/24? Should be just under 0.5.
It's 0.14.
No, it's not 0.1.
Not 0.41.
5. 10/24. What is it?
0.41.
0.416.
25/60ths?
Same thing.
Oh, look at that. Very cool.
Did you say 6 at the end?
Yes.
Alright. So let's talk about Gabe's saying it's proportional for him to get most of the food.
Oh, yes.
What's it proportional to? You have to have an equivalent fraction on the other side, or ratio.
My belly is 10 109 hungry, so you get all of the food.
Okay, we'll keep
It's
thinking.
a wild fraction.
Yeah, alright. And now we have some variables in here. So, if you look, none of these just that are showing are like what we had a second ago. Like, let's do an easy one. 5/10 equals x over, actually let's put x on the bottom this time. Like that. What is x?
40.
Okay, so that's because you knew that this is, the numerator is times 4, so the denominator is times 4. Okay, if you look closely at these, none of these probably you're gonna do that in your head. Yeah. So what's a good strategy to solve a proportion? Yeah.
Cross multiplying by.
So I'll say cross multiply, and then the division part will be dependent on the problem. Okay? So I feel like we've talked about this, so maybe take cross products, which means diagonal products. Guys, the theory behind this is if we set the denominators equal, so let me move those green x for a second. I would need to multiply this one by 8, and of course the numerator by 8 to keep it equivalent. And let's get rid of this one. Nope. There we go. Then over here I would need to multiply by 10 over 10. Okay, so that would give us a denominator of 80. And we'd get 100, and over here we'd get 8n over 80. So now our denominators are equivalent. Everybody follow that? Which means I can ignore them and just mess with the numerators. Okay? Only address the numerators. Okay? Because if the denominators are equivalent, that means I could multiply both sides by 80 and it would be gone on both sides. Okay, so this really boils down to 100 equals 8n, and then, okay. So that is the mathematical workings behind what Nate said, which is to multiply diagonally. Okay, if you notice, we multiplied the 10 by this 10, and the n by this 8, right? So if we multiply diagonally, we'll get 6x equals 90. And our numerator our denominator under both would be 60, but we just ignore that, right? We'll just not worry about the denominator. Okay? So, diagonally multiply. And then he said cross multiply and divide. In these simple ones, yes, the next step is divide. But we're not going to do very many of these simple ones. So don't. Just remember the cross multiply and set equal. That's what I want us to remember. All right, let's take a break. So this one, pretty basic. You could have just seen that it was doubled and doubled, but okay, next one. Still also pretty minor. Some of yours will be this easy, which is nice. But the thing to be careful with on these kind is to put the b minus 1 or whatever your denominator is like that in parentheses. So you remember to distribute. Okay? And then go ahead and solve this like a normal equation. What is that? 51. And 51 divided by 9. What was it?
5.6.
Oh, yeah.
5.6 continuous. Yeah. That would be it.
Okay, so those really the same strategy. The nice thing about this cross multiplying and setting equal is that it works with all these, but the steps that are required to solve afterwards sometimes require a little bit more work. So if you're looking at these two have variables in 2 places. So if we compare that to what we just saw, variable in 1 place, variables in 2 places now. Any difference in the strategy? Nope. So take your cross product. We'll get 9b equals 7 times b minus 10. And like I said, it's just a difference in the steps required to solve from there. Okay? But otherwise, it's the same process. Any questions on those guys? Okay. Those are just bigger numbers. And then we'll get to these kinds. And we'll put an example and write some notes about this. But what is different about this now?
You're multiplying 2 variables.
Yeah, so we're gonna get a quadratic in these, okay? Still, the setup is the same, we're gonna cross multiply and then set equal. But in these kind, we're gonna end up with quadratic. So let's go ahead and use this as an example in one of your boxes. That's not it. And to save some room before you, it sounds like you already flipped there. So,
Hey, can I get another notes back here?
can you get what?
I need notes.
I guess we'll go back and add the note to the front in a second. So, go ahead and write that. And we're going to call this solving proportions. All right, so we're going to say multiply diagonally and set the products equal. Now, obviously there are some that you don't have to do that. You can just do it in your head, but most of the time it's going to work out this way. By the way, sometimes people call this the butterfly method. Because if you do that, it kind of looks like a butterfly. Okay?
Maybe you have to draw the little thing.
Like antennas and stuff? No, I'm not. Okay, so put everything that's an expression or a group in parentheses. Step 2, solve using normal methods. Depending on the type of equation. So this one is going to be quadratic. We're going to get n squared. I don't know if I should need to do this, but I'll put it there anyway. Okay, so n squared, and then we'll get negative 4n plus n, which is negative 3n. Okay, what's next?
You want me to get rid of this?
Go ahead, Nate. Well, even before that, you need to ask, is there a bx term, right? Because if there wasn't, don't write this, of course, but if this wasn't here, I would not need to subtract the 50, but add the 4, so that we split and get this n squared by itself, okay? So since there's a 3n, yes, we'll subtract the 50. But maybe write that reminder, is it, no, it's not wrong, okay? Is there a bx term? And then if it's yes, we're going to square root. Sorry, if it's yes, we're going to factor or quadratic formula. If it's no, you're going to square root. Let me, up here, I'm going to put for quadratic. I think the last time you've had notes on that, as a reminder, was the first unit, which has been a while. So it's good to have this here again, because you'll certainly come across some quadratic problems in this unit. Okay, so we do have a bx term. Let's subtract the 50. I feel like that should be added in here. So, hey man, set equal to 0, factor, just stick it in there, like put a little arrow if you want.
Good thing I did.
There we go. Set equal to 0 first. Are you still mad?
Yes.
Okay.
No, it's not because I did it
Well, you're lazy.
right. I'm ready. Four.
Alright, and then we'll star this. Star says A times C, B, A and A. Are there factors of negative 54 that add up to negative 3?
Absolutely not.
Negative 9 and positive 6.
I was just joking. I was thinking
And then we get x plus 6 times x minus 9 equals 0. And then we'll get x equals negative 6, x equals 9. So either one of those work. If this is a triangle that you're solving, you're going to need to check if they both work. In fact, let's write that reminder. If this was a linear equation, it solves the same. The solving step is different, but the idea of what we do next is the same. So cross multiply, set equal, and solve as usual. Any questions on this? Do you want to do one? Just to give it a shot? Okay. So go ahead and do that one on the right. 5 minutes.
Where the fucking lines come from?
What are you saying right there, Cooper?
He's
Yeah.
here. They're here. You multiply together with 3 and add together with 2. The only thing you can do with that.
But it's just 16.
Well, you have to add this negative 12 over here to it so you can set it to 0.
Numbers like this.
So then, positive 12
Since
plus
I'm doing
negative
numbers
15
just up here.
negative 3.
Alright. Everybody good on that?
Just random numbers being out of the-
Okay.
You have to set
Yes.
Or
Okay, so Al, he's asking if both, whether it's this or on our example just now, will both work? Algebraically, yes. Okay,
Yeah.
meaning these will both make these two ratios equal.
But geometry.
But in geometry,
We can't have
if
that
this is
negative.
a side length, that negative or the negative 1 wouldn't make sense because this would be saying that side length is negative 4,
Negative 6.
negative 6.
So for like both of those variables, we got both of them.
No, not necessarily. I'm saying in this problem it wouldn't, but in a different one it might. Yeah. So that's why we check. But algebraically, these will always work.
The 3 is still technically wouldn't work.
Yeah, he's right actually. In this one, the 3, if this was a side length, it wouldn't work either.
So are these problems that we're doing, are they already similar, or is this list trying to figure out if they're
It depends. Sometimes you'll be told that the two figures are similar and you have to solve for x. Sometimes you'll be checking if two figures are similar by checking ratios. Sometimes you'll solve for x to make them similar. So it just depends. All right, let's get into this then. All of that was review of proportionality. So let's talk about what similarity means and scale factor and stuff.
So was that the easy stuff?
It's all I think you're gonna find pretty
So it was?
relatable.
All the stuff that
No, and it's not necessarily. I'm saying I don't necessarily think it gets much harder than that. It's
Well, that's what I thought.
it takes some practice to see things in this unit for setting up the proportions. So I guess by that definition, that was the easy stuff. Because, yeah, I guess I should say this. Guys, we just focused on solving. The bigger issue in this unit is setting up the proportions correctly. Okay? So that's kind of where we're headed next. Alright, I'm going to skip that. So, have you heard the word dilation before?
Yeah.
Like your pupils dilate?
Yes? Sure, it's the same word. But what do we typically think of when we say dilate?
Bigger.
Yeah, like when you're talking about your pupils and we say dilate, it means they're getting bigger. And then for the opposite, in terms of that application, we say constrict. So pupils are constricted or dilated. So if you just did some heroin, your pupils would be pinpoint, we call them, super constricted. What?
How do you even know that?
Example.
How do I know that?
Did you know that when you see someone that you like, your pupils get bigger?
Okay, so if you look at Jazzy and her pupils are really big, she's probably digging on you a little. I'm just kidding. Dilate. We have. How do I know that? Well, because I was an ER nurse for a while.
Why did you do this? Did you not like the guy?
It's a long story.
Did
Anyway.
you get hurt in the field?
No. So dilate in math can mean bigger or smaller. That's the big thing you need to take away from that. Okay? We use the same word for both. So a dilation is not just bigger. How do we make something bigger or smaller? What math process do we use? Or what?
Square root.
Okay.
Scale percentage.
Okay, so he's saying specifically we could square it or square root, true. He's saying we scale each dimension up or down. Scale means what? Multiply. Okay, so we're multiplying. That's probably the big concept from this, is multiply. How do we multiply and make something smaller? Yeah, it has to be between 0 and 1, the number that we multiply by. Okay? So let's talk scale factor, or just start introducing that concept. And I guess real quick, notice the notation. The black rectangle is the original, and it's A, B, C, D. The new, what we call the image, is with prime notation. So A prime, B prime, C prime, D prime. Anyway, what did we multiply AD by to get AD prime?
3.
Well, this is 2 and this is 6. So times 3 is what we scaled this up by. Okay? What if we went the other way? It's still a dilation.
Is it 1 over 3?
Yeah, we just flipped that thing over. So now it's 1 over 3 to get AD prime. I guess I just need to write that. Or excuse me, to get back to AD. What are you confused about? What are you confused about? Okay. So direction is a really important idea here. Make sure you read carefully. Are we talking about black to orange or orange to black? Okay. And it will say either the two figures will have totally different names, so you know which direction, or it will say big to small, small to big, something like that.
Have you ever seen that show?
What?
Orange is the New Black.
Should it be the same here?
Yeah, I mean, depends if it's consistent, right? I think so.
What is the word that you're looking for there?
Proportional?
Yeah.
There we go.
If these two figures are similar, then the two sides should have the same, they should be in the same ratio, right? Otherwise something changed and it looks weird. Okay. Alright, so how are the side lengths and angle measures related? I guess that was here too. What about the angles? Are they different in these two figures? Okay. I guess before we get too far into this, I want to ask you to remember the word congruent. What did it mean? Or congruent?
Equal to.
They're like the exact same.
Exactly the same, right? Like carbon copy, stamp. What does similar mean, just in general?
Basically, it's
Roughly the same.
Yeah, but does similar mean the same?
No.
No, it doesn't, right? If two things are the same, we say the same, or in geometry, congruent. If two things are similar, we do not call them the same, right? So can two similar figures be exactly the same? Okay.
Wouldn't the angles stay the same whether you
Yeah.
make it bigger or smaller?
Angles should stay the same though, right? Like he said, whether we increase the size or decrease, the angles shouldn't change. Good. So same thing. What's the scale factor from black to orange?
Violet.
Cooper.
and like two boxes in the orange.
Yeah.
Can you see the dots at all?
Yeah.
It's the same, right? So we kind of did this already, but
Dilated by 0.3.
well,
Well,
0.333 or a third. Okay. All right, these are good. Let's move on. Okay, so scale factor is this thing that we've been talking about that you multiply by. Okay, we'll define it in a minute. What is the scale factor from original to image or black to orange? What's the scale factor?
Between
One.
1/2. What's the scale factor from black to orange here?
Absolutely.
2/3.
That would be from orange to black, would be 2/3.
3 seconds.
Okay. So you're kind of picking up on being able to flip-flop, like to take the reciprocal, right? So if orange to black is 2/3, black to orange must be 3/2, right? 3/2 or 1/5. So how do we find that scale factor? Well, take your destination. I don't want to use that word. Let's use the word new. New figure. Figure
Oh, and then just
over
divide.
original,
Okay, yeah.
which is 18/12, right? That's our scale factor. And then if we simplify that, it's 3/2. That's all. Just divide where you're headed. That's why I was going to write destination. Destination divided by origin. And you got your scale factor. Okay. Trying to decide if I want to do this. Here's the question, what it's asking. How should those two lengths be related? I know I didn't write it out very clearly, but those two lengths. How should they relate to the scale factor? The same, right? I mean, they should be multiplied by the same thing as any side lengths do. So let's check. Well, let's pick an easier point, I guess. What's the scale factor from black to orange? Times what?
3/2.
Times 3. So how far is P to A?
2.
2. So how far should P to A prime be?
6.
Yeah. Okay, so this is times 3 as well. 1, 2, 3, 4, 5, 6. So distances on the coordinate plane should also change by the scale factor, assuming that all we do is dilate. Okay? Good on dilations, what a dilation is. Let's go write some stuff down that we've just been looking at. Also, I told you I wanted to write just a reference to this example. And this is all I was going to write. Okay. So enlarging or shrinking a figure by the same scale factor in each dimension I suppose it's worth underlining or shrinking, just because we are used to hearing dilation mean strictly to grow something. Okay, let's talk about scale factor. You know what, before we do that, it might be nice to just show a little picture for what we're talking about here.
Picture.
Okay, so scale factor is the number let's say it this way. Emphasize the word multiply. How could we word this? So it's the new, but it's not always going to say the new figure.
We can just use.
I think I'm going to use that word destination. Just because it makes sense. Because we're going to go both ways, so we're not going to have a new and an old figure. Make this a little formula. You'll probably pick this up pretty quickly to where you don't necessarily need to reference the formula, but it's good to have it for the first few times. You'll have to let me know if you want an example of finding scale factor after we do a few more of these, but let's start looking at similar first. So are Fords similar to Chevys? What do you think?
In some ways.
Depends on the model.
Okay. Definitely depends on the model.
Like the engine doesn't
Let's say we compare Ford trucks to Chevy trucks. Just pick a model.
Chevy
Similar.
surviving.
What?
Chevy won't break down on the side of the road.
Okay. Is Popeye's chicken similar to KFC or what's the other one here? Roosters? Is there a rooster?
I don't know, I
Yeah.
haven't had either.
I know.
Over closer to Fruit like in
Well, I've had this before a long time ago. But.
Popeyes are
What do you think? Remember we said a bit ago that similar does not mean exactly the same.
So they are similar.
So some piece of chicken meat's deep fried or fried in some kind of batter with spices, it's similar, right?
Should I ask if the great value version of Pop-Tarts is the same? Or similar to Pop-Tarts?
How about that? Are they?
Yeah, they're similar.
Yeah, they're similar.
Any
Okay.
great value.
Let me know if this is too small. Kind of looks small.
Yeah, what is the dimension?
So it says which reindeer is similar to Papa? This is Papa. It says Papa, but I know you can't see.
those antlers are crazy.
Which one is similar?
Is the
They're
bottom
both
one just
similar.
squished?
Are either one of them similar?
No.
None of them.
Well,
No.
One of them looks
I mean,
squished and the other one looks
It's
stretched
literally the same exact one.
Squished and your life.
Why are they not
It's a
similar?
weird
They don't
And the
have
dimensions are not the
similar
same.
dimensions.
The dimensions changed in different ways, right? This guy's got squished vertically, and this one's squished horizontally.
No.
Okay, let's make this bigger. Okay, we have a mama bear, and then 3 babies.
Bear 3.
Are there any similar bears to mama bear?
Bear 3 and Bear 1.
Wow.
One.
They're
Bear
just bigger or smaller.
They were tiny.
I think bear one
Bear
is the
one.
most similar.
Oh wait, Bear 3's a little squished.
Actually,
Not
not
by a
Bear
lot.
3, because he looks like elongated vertically.
Bear 3 does?
Bear
No,
3
Bear
does
2.
not look elongated.
Bear 3 is.
Bro, I can't even tell the numbers, bro. I thought that was.
There's
Bear.
no number. Oh, this is 2, this is 3.
Yeah,
There is
Bear
definitely
3
not.
looks
Okay, so
like-
think about in terms of scale factor, mama to bear 1 was probably like, I don't know, half or 2/3 as tall and wide, right? But to bear 3, probably a little taller, but not any wider. So that is, it looks funny, right? Similarity shouldn't look different other than size. That's the only thing that should look different. Your eyes pick up on it. How about kites? Do those look similar?
Yeah.
Okay. Just a different size. That should be the only thing that changes when we have similar figures. Okay? And you guys have all done this. In fact, you just saw me do it. If I wanted to change the size of this picture, I could do that. Is that similar?
No.
Because I only changed one dimension, right? Same thing this way. Like I could only change the left and right dimension. So it looks different. How do you make it be the same?
You have to use it and draw it out.
I have to change both dimensions by the same. So it's going both vertical and horizontal. Okay? You've all done that, right? Probably 8,000 times dealing with photos. Alright, you've spent most of your childhood surrounded by similar figures, in fact. Simple way to think of them is an object that's either shrunk down or enlarged, and then looks the same otherwise. Like
Hey,
a
look, it's-
toy car,
It's my
right?
Barbie girl house.
Yeah, that's yours.
Yeah, I lived there for a minute.
When you play with one of those toys, it doesn't look squished in any dimension. It just looks smaller, right? Now, Barbie herself is kind of an anomaly, but we won't talk about her.
An anomaly?
Yeah.
See that CP?
This one's kind of interesting. Giant miniature fun fair. So it has some words. So, miniature wonderland in Hamburg, Germany. It's a real place. It says it claims to be the biggest train layout in the world. Anybody a train fan?
Used.
Okay. They posted the scale factor as 1 to 87. So that means everything in the model is 87 times smaller than in the real world. Okay. So if you're 5'6", is anybody 5'6" in here? We have some of you that are probably close.
Wishing.
Yeah, like,
Okay.
oh wait.
Which we will think of as 66 inches. So if we divide that, or do 66 times what? Remember we said scale factor is multiplying.